Hello, Gary Parker here. We're going to take a look at an activity for math for elementary school teachers. To do that, I've got some toys to play with. So I have these squares, color squares, sometimes they're called color tiles. And alternatively, there's an app, if you don't have your own squares to play with at home, where you can drag the squares onto the screen to play with. And they kind of snap together when you mess around with them. And for this activity, color doesn't really matter. You could use the same color or different colors. And third option for playing around with this stuff is you could just draw them out. Like suppose I wanted to mess around with 5 squares. So I could just draw 5 squares in a rectangle. And one way to do that is a rectangle that is 5 by 1. Another way to do that is vertically. And I can draw out 1 by 5. So you either need some blocks or some scratch paper to mess around with. The goal here is just to play around and see how rectangles from blocks and factors are related. So for example, for the number 5 for 5 blocks in my picture here, I showed that I could make a 1 by 5 rectangle, and I could make a 5 by 1 rectangle, but there really aren't any other options. So sometimes the physical toys are fun. So I could just play around with 5 of them here. So let's see, I think there's 5 blue ones. And I could put the 5 blue ones together like that, but that's not a rectangle, right? So I can put the 5 blue squares together in a lot of different ways, but that's not a rectangle either. So the only 2 rectangles I can get when I play around with the 5 blocks are this one right here, 5 by 1, or this one right here, 1 by 5. And this is a game for young kids, because this is really going to be an exploration where they're like, hey, look at my rectangle. And some other kid's going to go, hey, that ain't a rectangle, dude. And that is an important exploration and discussion that people can have, and that this rectangle is different than that rectangle. If we consider base versus height, base of 1, height of 5, base of 5, height of 1. If these were buildings, they'd be different looking buildings, right? So the activity back here, I give an example of working with 4 blocks, and I found I could do it in 3 different ways: a 1 by 4, a 2 by 2, and a 4 by 1. And so I'm just going to play around. We're going to repeat this idea with each of these number of blocks here, either thinking it in your head using physical squares or blocks, or using the virtual ones, or drawing it on paper. And eventually you want to fill this out. And you could either fill this out on paper, so you have it written down like I have here, or maybe you could copy and paste all of this stuff into a document, and then you could type it out in the document here. So for example, I can fill a 5 in here. And here I'm just using an X to show multiplication. If you'd rather use an asterisk, that's cool too. Communicate it somehow. But I found there's 2 different rectangles I can make with 5 blocks. So keep filling that out for the rest of them. And then there's some questions to answer about that, the stuff that happened above. The other thing that we're going to look at here is the factors of a number. And so we'll play with that in a slightly different way. So we'll do that right now, I suppose. So either you have to have something to type into, or you have to have something to write on, like a piece of paper, where you draw that out. So let's pick on 5. What are the factors of 5? So one way to find factors is to make a factor tree. And so the way that works is starting with the given number, you say, okay, what numbers divide into this? And I could say, well, 1 certainly divides into 5 times, but otherwise nothing else divides into 5. So 5's factors are 1 and 5. There are 2 factors. If we try that for a number like 8, let's try 8 here. Let's see, 1 goes into 8 times. And then I'll move up to 2 goes into 8. How many times does 2 go into 8? 4 times. And 2 goes into 2 by 4 2 times, right? When I make a factor tree, the ends of the branches, here and here, here, and here, and here, and here are numbers that I can't factor any further, is the way you do a factor tree. And if you can't factor any further, you get one of two things. The numbers at the end, so the ends, are either one or a prime number. And one is not considered prime, by the way. Something is prime if it has exactly two different factors, no more, no less. And sometimes when we make factor trees, we only do prime numbers, we don't put one in. I just put one in there for the heck of it. So I've discovered some of the factors here of 8. Another way to come up with factors is to make a factor pair list. And the way that works is, given some number like 8, we write down pairs of numbers that can be multiplied to give us 8. So the simplest one is 1 times 8. Next one I could find would be 2 times 4. 3 doesn't work. 4 I've already got covered, so I'm getting a repeat, so I'm done. So these are all of the factors. So I'll try that again for a different number. Let's try it for 12. 1 times 12 is the first pair of factors. If 2 goes into it, try 2. 2 times 6, try 3. 3 goes in there 4 times. Next number to pick would be 4, but I already have 4 in my list, so I'm done. And sometimes these lists are pretty easy to make. Sometimes it takes a bit more work. Like suppose I tried to make one for 51. So let's see, 1 times 51 is one option. 2 doesn't go in because it's odd. 3 does because 5 plus 1 is 6, and 3 goes into 6. So 3 goes in there how many times? Well, 3 goes into 5 once with 2 left over. 3 goes into 21 7 times. So then 3 goes into 51 17 times. You could double check on a calculator. 4 is not going to work because it's odd. 5 doesn't work because it doesn't end in a 0 or 5. 6 doesn't work because 2 didn't. 7 we actually have to check. And I know 49 is close to 51, and 7 times 7 is 49. So 7 doesn't work. 8 doesn't work because 2 and 4 didn't. 9 doesn't work because 5 plus 1 is 6. What's next? 9, 10 doesn't work, obviously. 11 doesn't work because multiples of 11 near here are 44 and 55. When do I stop looking? Well, one answer is you stop looking at 17 because that's a number I already know. So I'm going to keep going. Where was I? 11. 12 doesn't work because 2 didn't. So really, because 2 didn't, I don't have to check any more even numbers, actually, based on one of our rules of factoring before, or divisibility. So let's see. 13, we actually have to check to see if 13 goes in there. So whip out a calculator or write down, does 13 go into 51? Let's see, 26, 39, it would go in 3 times with a remainder of 11. So no, 13 didn't work. 15 goes into 45, but not 51. 16, nope, and then I get to 17 and I'm done. So sometimes there's a long gap between these two. It turns out there's another point to stop, but I'll talk about that later. So sometimes it's easy to find the list, sometimes it's a lot of work, and a calculator could be handy. So your goal here for this activity is to just fill out the table about rectangles after you play with some rectangles, and then the number of rectangles that we found for each number. List all of the factors of each number and then how many there are. And then there's a few other numbers I'm going to ask you about, like 24, 51, just did that, 53, and then there's some more questions to answer. So if you get stuck on any of these questions, ask a classmate or ask me next time in class. That's it for now. Take care. Do good math. Bye-bye.